Hi Mom, welcome to this video where I'll outline what your favorite child research is and how she's going to be spending her foreseeable future in grad school. Let's start with a little background information and terminology. Atoms are what things are made up of. Atoms have a core, which are positively charged, and negatively charged electrons orbit this positive core. We can also have molecules which are atoms that are bonded together, like water, H2O, or carbon dioxide, CO2. So what is plasma? You're probably thinking of blood plasma, but I'm thinking about the fourth state of matter. The scientist that coined the term plasma named it after the Greek word for moldable substance, or jelly. Starting with the first state of matter, we have a solid. The molecules are bonded to each other in a uniform pattern, and the more energy we add, the overall object melts, and we end up with a liquid. As the forces between the molecules weaken, adding even more energy, the bonds between the individual molecules break apart completely, and the object vaporizes, becoming a gas. If we keep adding more energy, the gas molecules will ionize, meaning that molecules will break into individual atoms and electrons are removed from these atoms. Now we have a plasma. A neon sign is a great example of a plasma you might encounter in everyday life. Other examples are the aurora borealis, the sun, and the lightning bolt. When you rub your feet against the floor and touch another person, the shock you feel from the static electricity is plasma. The difference in safety between the lightning bolt and the static electricity is the amount of energy moving through your body over that time span. A lightning bolt is dangerous because it has a lot more energy, so that amount of energy in the plasma determines its safety to humans. One way to utilize plasma is as a fuel source for in-space propulsion. Electric propulsion, or EP for short, is the use of electrical energy to accelerate plasma as the fuel. EP is used only in outer space because it creates very little force, as much force as a piece of paper on your hand. This works great in space where there's no gravity, but it's not practical for a rocket that launches from Earth's surface. Satellites that use electric propulsion use less fuel than other types of propulsion methods like chemical thrusters. This allows satellites that use EP to operate for a longer period of time. Therefore, EP is ideal for deep space exploration outside of our solar system. The first electric propulsion thruster flown in space was in 1964, orbiting around Earth to prove that EP systems would work in space. Another famous NASA mission that used EP was the Dawn mission, which used it to propel the satellite to an asteroid belt. One type of commonly used electric propulsion thruster is called a Hall thruster. Elon Musk, the founder of SpaceX, is launching satellites into space for faster Wi-Fi. All these satellites use Hall thrusters for maneuvering in orbit. Hall thrusters operate on the principle of a force called electromagnetic force, which is where both an applied electric field and a magnetic field are applied in order to accelerate the positively charged ions out the back of the thruster. The electrons gain what is called the Hall current, in which they begin spinning around the middle section of the thruster due to the interaction between the electric and the magnetic fields. The gas atoms are ionized when the spinning electrons hit them. The electric field accelerates the free ions out the back of the thruster. As an ion leaves the thruster, it attracts an electron, so there is no large charge buildup anywhere on the thruster. Hall thrusters are a proven technology that has flown in space. They are mainly used on missions for maintaining a specific orbit and changing the altitude of a satellite's orbit above the Earth. Another type of electric propulsion in development is an electron resonance cyclotron thruster, or ECR for short. An ECR thruster uses a magnet to move electrons in a circular path. An antenna then inputs microwaves, similar to those used in a microwave to heat food, in order to match the movement of the electrons. By matching the movements, the electrons move faster, which then causes them to heat up and create plasma. The plasma is then accelerated out the back of the thruster, which again propels the thruster forward. The advantage of ECR thrusters is that they don't need an external source of electrons, making their design much simpler than that of a Hall thruster. After learning about the physics behind an EP thruster, using computer simulations to predict its performance, and building a thruster, we can now actually test a thruster. Testing is an important part of the process to see how electric propulsion, like Hall thrusters and ECR thrusters, perform. This takes place in vacuum chambers that simulate a space-like environment by pumping out all the air inside the chamber. Some vacuum chambers can get lower than 1/1,000,000th of the atmospheric pressure of Earth. When plasma is shot out the back of a thruster, it will cool, since it's no longer receiving energy and will reform into a gas. There are many types of measurement tools that can tell us how hot the plasma is and how fast it's shot out the back of a thruster. All these measurements can help us predict how a thruster will perform in space and how efficient it will be. However, this is only a prediction because in space the operational parameters are different. There are no vacuum chamber walls surrounding the thruster, which alters its performance slightly. The process of designing and testing these thrusters is a great mix between engineering and physics. We need to understand the plasma physics principles that make the thruster work and also have the engineering skills to design a thruster that will work. Thanks for watching. I hope you learned a lot more about plasma and electric propulsion and have a better understanding of this sector of aerospace engineering.